Our next lesson on solids starts out with pyramid. If you take a prism, chop the top face off, and then have all the edges, all the lateral edges, collapse to a single point, you end up with a pyramid. Here I have two examples of pyramids. Here's one with a quadrilateral base. This point at the top we call a vertex, the pyramid's vertex. That is the point where all of these lateral edges meet at. Here is a pyramid with an octagonal base. And again, you can see that all these lateral edges meet at this top point. Now, a prism had two base faces. A pyramid will only have one because there really is no ceiling. You can think of the ceiling as a single point, not a polygon. So a pyramid will only have one base face, one base polygon. And with a prism, all the lateral faces or parallelograms. With a pyramid, all the lateral faces are triangles. And the number of triangles will equal the number of sides that the base has. Quadrilateral has 4 sides. There are 4 triangular walls here. With the octagon, we have 8 sides on the floor, 8 sides on the base, and then we will have 8 triangular walls. There's really no rule what the base has to be other than that it has to be a polygon. That is it. The base is some polygon. The lateral faces are all triangles. Each triangle has what's called a slant height. We use little a, that's actually incorrect. Now that I see that. That should be the letter L. We use an L to represent slant height. Capital H is the height of the pyramid. And I will illustrate those on the next screen. Think of L as the height of each individual triangle. It's called slant height because this triangle is slanted. It's not straight up and down. If you've ever seen pictures of the pyramids, you'll note that those triangles, those triangular faces, are tilted. They're tilted back. They sort of lean back away from vertical. That's why this is called a slant height. That is the height of that particular triangle. And here's what they look like. You see the vertical height here, capital H, that is the height, that is the distance from this vertex straight down to the center of the base. It's that point straight down to the middle of the floor. That is what we use for capital H, and we will need that later when we talk about volume. For surface area, we need this slanted height. We need the height of this particular triangle. Lowercase l, that is the slant height. Same thing over here. Here's the height of the pyramid in green. Here's the height of this particular triangle in red. That is also the slant height. I need to go back here. One thing to keep in mind, if all of these triangles are the same, then this is going to be a regular polygon. And I should have said that the other way. If the base is a regular polygon, all of these triangles are equal. Now, let's come over to this one. Let's say this is a rectangle. So let's say this side is different than that side. This triangle here, this face, will not be the same as this, as this face. Undo that. So if I were to put some numbers here, say that's 8, let's say that's 10. So this triangle has a base length of 8. This triangle has a base length of 10. Their slant heights, though, must all be equal. All of these triangles, all 4 of these triangles, all 8 of these triangles must all have the same slant height. You cannot have a pyramid with different slant heights. That would look really weird if that was the case. All the triangles along the lateral faces, all of those triangles have to have the same height. Let's look at the surface area of a pyramid. Just like a prism, there is no one formula that works all the time, because the base of a pyramid could be any polygon. So it cannot be just one formula every single time. It will always depend on what your base is. If you have a square base, then your base area is the area of a square. If you have a trapezoidal base, then it's the area of a trapezoid, and so on and so on and so on. It all depends. The lateral is simply find the area of each individual triangle, add up all the triangles. And also remember, if you have a regular polygon base, all those triangles are congruent, because we already know their heights are the same. And if that base is a regular polygon, we will know that all the base edges are the same. So when we're finding the triangles, it's 1/2 base times height, and all the bases and heights are equal. If it is not a regular polygon, we have to look at them separately. Before we move on to some examples, just like a cylinder is similar to a prism, a cone is similar to a pyramid. It's not a pyramid, though, because the base is not a polygon. It's a circle. Here's that slanted height again, L. And here's a common misconception. A lot of geometry students assume and believe that a cone is created from a triangle. Just like if you take 6 connected squares and you fold them a certain way, you get a cube. That's sometimes called a net. A net is, if you were to cut that solid and lay it out flat, what are all the individual shapes? What do all the individual shapes look like? What do all the individual polygons look like? Well, some people think that the net for a cone is simply a triangle, and that's not true. The base is a circle, but the lateral area is a sector of a circle. So the net looks like this. It looks like a circle with a slice of pizza attached to it. This arc right here wraps around that base. So this arc here becomes this circumference. And then as this wraps around, these will eventually come together and form that cone. So you are basically using 2 different circles here. You have one circle, that's the base, and then you have a different circle that creates the lateral. Only it's not an entire circle, it's a piece of a circle. It's a sector. This would be the center of that circle, and the slant height would be that other circle's radius. And that's going to be key when we see what the formula for this is. So here's that same net with a little more detail. So I labeled this piece the lateral area, LA. That's sort of the wraparound part of the cone. Here's the base circle with a radius that I called R. I labeled this point A, this point B. So here's arc AB. It has a measurement in degrees that is equal to this angle. It also has a measurement as a distance. So it has an arc length. And that's 2 pi r. As this, again, this will fold around the circle. So this arc A to B will go completely around the circle. So this circle's circumference is equal to this distance. And then here's our slanted height. L for the cone, it's also the radius of this circle. So we got a lot going on here. We're going to come up with a formula to find surface area. So here we go. I know that the arc length of AB, we're going to ignore this part for a moment. So let me just slide this. Yeah, we'll just focus on this part here. We know what this area is. It's pi r squared. We're trying to find this area. Okay? So, we know that to find this arc, it's whatever that angle is, divided by 360 times the circumference of this larger circle. We're ignoring the 2 pi r for a moment. We're just going to pretend that this circle is not here for the time being. You just focus on this arc as a fraction of this larger circle. So we know the arc length is the fraction of the circle times that circle's circumference. That's equal to the distance from A to B. So what I did is I rearranged things a little bit. I divided both sides by 2 pi L, which is the radius of that circle, and I get this equation here, x over 360 equals the arc length over the entire circumference. And that really is what arc length is. Arc length is a fraction of the entire circumference. Now let's look at this as a fraction of the entire circle's area. And we may recall it's the same fraction. Whatever x is in degrees divided by 360, that gives us the fraction that this represents, but now it's a fraction of the entire area. Again, we're pretending that there's a completed circle here. Area of a circle is pi times radius squared. The radius of this larger circle is L. That's the lateral area. That's this entire piece. And again, it's a fraction of the whole circle. This angle is a fraction of 360, and that's the same fraction as this is to the whole entire circle. Now I have two fractions that equal the same thing. That means these two fractions are equal to each other. And our goal is to get lateral area all by itself. So before I do that, I'm going to substitute 2 pi r in for AB. Now we bring this circle into play. We know that this circumference is equal to this distance. So I'm going to plug 2 pi r into this spot. And I can see that the 2 pi's will now cancel. You can do a little cancellation there. and we end up with R over L equals lateral area, which is our goal, over pi L squared. Well, let's cross multiply. We're not ready for you yet. Let's cross multiply. L times lateral area, and then here we get R pi L squared. And now what I can do is divide both sides by L. So this L goes away. This L squared gets knocked down 1 power and becomes pi R L. The curved part of a cone, that lateral area, if you think of it as being the wrapper of a cone, or if you've ever gotten an ice cream cone and there's a little paper wrapper around the cone part, that would be the lateral area. It is pi times the cone's radius times the cone's slant height. So, putting this all together, surface area of a cone. Here's the base area, the circle that the cone sits on, pi r squared, and then we have pi r L, lateral area. Just like with a cylinder, we had an alternative formula. We have the same thing with a cone. We can factor out a pi r from each term and have the cone surface area be pi r times r plus L. That is surface area of a cone. Now we're ready for some examples. Here's a pyramid. Let's find the pyramid surface area. Here's its base. Here's one lateral, and then here's a lateral face in the back. So we have what's essentially called a triangular pyramid. The type of pyramid is what kind of base does it have? If it's a triangular base, it's a triangular pyramid. If the base is an octagon, like what we saw earlier, it's an octagonal pyramid, and so on. Square pyramid, the base is a square. Here's a triangular pyramid. Let's find its surface area. So, start with the base. The base is a triangle. This base shape is a triangle. Every triangle has a base and a height. Well, it says this is 15. It says this measurement is 13. So looking just at this triangle that constitutes the floor of the pyramid, it's 15 long here, and it's got a height of 13, both in inches. There's our base area, half of 13 times 15. And for this, a decimal's fine. Some of you are not putting your labels in. Make sure if there's a label given that you use it. 97.5 square inches. Let's find the lateral area. We have 3 triangles that make up the walls, but they are not all the same. They are not all the same. We need this right here and this right here. We don't have those. Or do we? In this particular figure, all 3 of those sides are equal. How do I know that? It was given from the source that I got this from. Now, let's say this was not given. Let's say this was not given as an equilateral triangle. How do we know they're all the same? Well, then we need to know what kind of pyramid this is. If it's a regular pyramid, that means the base is a regular polygon. If we didn't know that, then we would have to resort to some trigonometry to find what each of these missing sides are. So, something to be aware of. Don't just automatically assume things are equal. You need to be given those things. Since we know now that all three of these triangles are the same, we can find the area. 3 triangles, each triangle is half base height. The base of each triangle is the length of each of these. We know that each of these sides is 15 inches. This height is really L. Height of this triangle is the slant height of the pyramid. So instead of H, we could have used L. All of this then becomes the area of all 3 triangles, which appears it's going to be 25 square inches, if I did that correctly. No, that is not correct. That is not correct. 45, that's not even close. 45, 450, that should be 225. That's better. $225 square inches. I didn't multiply by 3, I multiplied by 1/3. Big difference. 450. Yeah, 225. Base area, lateral area, total surface area then, putting these together, 322.5 square inches. Still the surface area. Area is always measured in square units. And again, if you are given units, I expect units in your answer. On your last assignment, it was minus half a point. On the next one, it's going to be minus a full point if you ignore units. So make sure you pay attention to those. Next problem. Find surface area, and again, we will go terms of pi. So we will leave pi in our answer. Now you gotta be a little careful here because we're not given a radius, we're given the diameter. We have a radius, here's our slant height, and we're all set to go. Pi r squared plus pi rl. Since a cone has one formula, we can simply plug things in. R squared times pi, rl times pi, our surface area then, 64 pi, and that is square yards. Using that other formula, let's check that to see if, just to make sure it works. Helps if you write it correctly to begin with. pi r, that's 4 pi, times r plus L is 16, and it works just like the first one did. Either formula will work. Whichever one you are most comfortable with is the one that you should use. That is the surface area of a cone.